go back a little bit, when you're adding the two vectors together, technically, if we were to go to the original problem with the 30M angle 20, could you do the head to tail method just using those, or would we have to go through the rectangular method in order to get the two?
No, there are, okay, so addressing that. So if we did the head to tail, just started with what we originally started with. And the advantage of, I can do a relatively crude drawing just to have some sense of what my expected answer should be. So if I try to draw it correctly, so 20-degree angle, so that's 45, so 20-degree angle, something like that. And we'll let that represent 30 meters at 20 degrees. That is absolutely horrible there. Oh. 20 degrees. And now my second vector, this is my new starting point. It is a length 20, so it's about 2/3 the length of that, so it's going to be somewhere along there. And 40 degrees, that's about 45, so 40. Where that's 40 degrees, and that represents 20 meters. So head to tail method like that, and then my answer is a vector from where I begin to where I end. So I would expect my final answer to be that. So I have some sense of roughly kind of what the answer should be. It's somewhere around 0 degrees. I have it in the fourth quadrant here, and partly because I know it's going to end up in the fourth quadrant. This would not be sufficient for what's the sum of those two vectors if I wanted an actual answer, unless you're pulling out a protractor and a ruler setting up the scale, which is, I think, would be incredibly time consuming. Did I answer your question?
Yeah.
Okay. Now you can set it up this way if you want to, and then bring in law of sines, law of cosines, for those familiar with it. Because if that's 20 degrees there, that's 20 degrees there. So this angle right here would be, let's see, 180 minus 60, 120 degrees. And so you could use law of cosines to figure out what the hypotenuse is. And then from that, you could use law of sines to figure out that angle and then subtract 20 from it.
Okay, but you kind of need the components in order to find the vectors, like further to make it easier for yourself.
Personally, I find it a whole lot easier to put it in rectangular form first and then add them. Now, if you have a different way of doing it, that's fine. And Abigail, you had your hand up. Okay. I'm going to change the problem slightly. I'm going to keep the exact same problem. I'm going to change I hat. So let's make I hat to the left and J hat up. What's the final answer in rectangular form? We've done the hard work already. All I've done is switch it, I hat.
Would you change the I hat to like negative?
Yes. So the answer would be negative 43.51 meters I hat minus 2.6 meters J hat. If you wanted to write it, if you only want to write the units once because of some childhood trauma, you could write it also as negative 43.51 I hat minus 2.6 J hat, parentheses around the whole thing, and then meters. This is also an acceptable form. And since I got a minus sign, I could factor the negative out, so I could also write it as negative 43.51 I hat plus 2.6 J hat, close parenthesis, meters. This is also, these are all acceptable forms given that definition of I hat, J hat. Questions to hear? All right, I promised you a quick and dirty solution to at least one of them. So here's another way of doing the exact same, at least, let's take that first vector and break it up into rectangular form. meters, 20 degrees. Here's the quick and dirty into rectangular form. I define I hat to be in that direction. And so in rectangular form, it's 30 meters I hat. There we go, done. If I'm adding them, once I've defined I hat, J hat is perpendicular to that. That's what I would have to do for the addition is, let's see, it's 20 degrees, this was 40 degrees, so that's a 60-degree angle, not drawn as such. So 20 degrees, 40 degrees, so that's a 60-degree angle. That's 20 meters. And so I could break it up like this, if just making sure I define I hat and J hat based on a different system. It's a little bit harder to visualize unless you, I mean, for some of you it'll come naturally, for some of you it won't. I mean, we're so used to horizontal and vertical, but there's nothing that says I hat and J hat have to be horizontal and vertical, other than happen.
It's kind of like how in space there's no gravity, so therefore there's no up, so you can define it any way you want.
I would contend in space there is gravity, because why does the Earth go around the sun?
Is there, so I noticed on the test tube today, a lot of them were like, there is no friction here. There is no gravity here. Is there ever a place where that doesn't exist? Where that is actually true?
Within the realm of any of our experiences? Well, there's gonna be a gravitational force no matter what.
So gravitational force will always exist, okay?
Yes, and the only, theoretically, you could have a point if I had, that's now making up a universe. Theoretically, there is a point in which the gravitational forces potentially would cancel each other out. And if I've got two big masses here and two Earths, and I'm smack dab in the middle between them, being pulled equally in both directions, so the net gravitational force would be zero. In terms of no friction, there is something called the Meissner effect, which keeps one object from rubbing against another, but it requires that's what I'm looking for. It requires a superconductor, and there's still going to be air resistance. Whether you count that as friction or not is up to you.
I do. So the answer is no?
You would have to, in order for there to be no friction, you can't touch anything. So
You're gonna be floating in space, so the only way to have no friction is by also having no gravitational pull?
No, I could have gravitational pull and no
It
friction.
would just be in a vacuum, so no air friction, right? Like if it was in space.
Yeah. So if you're, in an everyday situation, you're in a vacuum chamber in free fall, no friction, then there's no gravitational pull.
Okay.
Actually, I thought that I made it sound like that, yeah, like such a place exists. Such a place does exist. There's a video that I have linked for one of the classes where Brian Cox does the, I don't know if you've seen the video of the hammer feather drop on the moon. One of the astronauts did it where they hammer and the feather, they dropped it, they fell at the same rate. There is a place, I think it's in Tennessee, I could be off on that, where they conducted the experiment of, they basically created this giant vacuum chamber and dropped, I think it was a feather and a hammer. They dropped two objects that, with air resistance, they definitely would not have fallen at the same rate.
Okay.
Other questions right now? All right, now I'm gonna take the exact same problem, except now I'm gonna put words to it to make it sound more like a physics problem instead of a math problem. I start from home and travel 30 degrees, 30 meters at 20 degrees north of east. I stop and then travel 20 meters at 40 degrees south of east. What is my displacement? Now it sounds more like a physics problem. It is the exact same thing that we just did. So, assuming that north is up, east is to the right. North of east, well, that's east, north of east would be in that direction, so that's my 30 meters, 20 degrees.
So just northeast.
If you just do northeast, because sometimes a textbook will write north of east or east of north, and it does make a difference. So north of east to me is more precise language.
Okay.
And then south of east, again, east this way, south of east is that way. And so this is the wording for that problem.
Okay. Just
Taylor.
one nitpick question. When it says north of east, and it is like northeast, it's just saying that because it's not due north, right?
It's not due north, and it's not, that's also 20 degrees north of east is the same as 70 degrees east of north.
Yeah, like I know it's
Okay.
not like northeast like on a map, but it's
Right.
just not due north or due east. It's somewhere in the middle.
Right,
Okay.
and if I said just northeast, that could be interpreted as at the 45-degree angle or anywhere in between.
Okay. Just clarifying.
Other questions? All right. Displacement, one of those words that I wrote up the other day as meaning vector stuff. So let's actually get into some better definitions. Slowly working our way towards the plus minus zero exercise. Yeah, it's coming. So chapter 2 is going to be dealing with, chapter 2 and 3 dealing with descriptions of motion. I think every physicist would love to teach chapters, the descriptions of motion and forces simultaneously, but you can't do them at the same time, so we do one then the other. Most textbooks will do the descriptions of motion first. Then in chapter 4 in our textbook, we'll get into forces, and then in chapter 5, we'll combine the two. But first, the vocabulary. Position. The symbol for, these are vector quantities. The symbol for position, there are 5 major symbols that are typically used for it. I tend to use X, but some people view X as always horizontal, and I don't. Y, Z, R, and S, those are the 5 main symbols. I tend to use X. R typically is used if you're talking about some central point and where you are radially from that. And S is also somewhat generic, coming from the Latin stadia, or stadium. Position is where an object is with respect to the origin. Now, the origin, the people who do maps typically put the origin at 0 latitude, 0 longitude. Doesn't have to be. I can make the origin where I woke up this morning. I can make my origin right now, right where I am.
WRT means which represents the.
Say it again.
What does WRT mean again?
With respect to.
Oh.
So the choice of the origin depends upon the person who's setting up the problem or solving it if it's not specified. Displacement. Displacement is basically two definitions. And they work together, but pick the one that's more convenient. It is the change in displacement, change in position, or where an object is with respect to the starting point. Change. How do we represent change?
Delta.
In
Delta.
capital delta, more specifically. And so the symbol is just the capital delta in front of whatever letter you're using for position. So, for example, I set up coordinate system, there's my origin right there. This is the initial position, so I'm going to draw a vector from the origin to there, x sub I. The subscript I, this is not I hat, this is subscript I for initial. Sometimes I might put a little 0 there for at time is equal to 0, or an O, which looks a lot like my zeros for original. But it's the beginning. I go from here, so picture a map here. This is, let's just say this is where the house is, and then I get to school. Let's say that's the school, so this is home, school. So my final position my final position is there. That should be an F for final. So my two X vectors here, X of I and X of F, both are where I am relative to the origin. There's a magnitude and a direction. The change is from here to here. That is the change in my position. It is also my displacement because it's where I am relative to where I started. Notice, if I'm looking at the overall displacement, it doesn't matter what happened in between. This is the nice thing about dealing with vectors is if I started here at home and then I did the circuitous route and ended up here, my displacement is the same as if I just went straight. And there are two types of displacement. There's instantaneous and overall. If I ask for what is the displacement without any qualifiers, this is the default overall. If I want you to tell me the instantaneous displacement, then I would have to use the word instantaneous.
And overall is just.
From the very beginning of the problem.
How is that different from instantaneous?
Instantaneous,
Wants me to map out all of the directions you want or something?
yeah, pretty much. So if I wanna know what is the, should not be writing with that in there. So if I wanted to, let's look at this point in time right here. If I wanted to know my overall displacement, then I'm looking at that vector right there. If I want my instantaneous displacement looks like that. It's where I was compared to where I just was.
So,
My
in
instantaneous,
reference to an equation, you have the first term, which is a vector x to the I, or under I. And then there's the next line, and if you want the instantaneous, it's just that from the last segment.
what do you mean by last segment? All right, so if I'm traveling
So-
around a track,
Can I explain again then? I'm gonna try. The peach line that you just drew
yes,
on the map, that thing, yeah. Instantaneous is that from home?
the instantaneous is where I am from the starting, overall is where I am from where I started. I started here. So this line right here would be the overall displacement.
Okay.
This right here is the instantaneous. It's where I was compared to where I just was a moment ago.
Like a very small millisecond kind of thing.
Yeah,
Okay.
mathematically, you let them, it's a little bit as time approaches zero. Right now, my instantaneous displacement is zero, because I'm standing still. My overall displacement from this morning is a vector that is several miles long at whatever angle. So position is positive if on the positive side of the origin. Think of a number line. You're in the positive numbers if you're on the positive side. So if I want to make that my origin right there, I'm going to be moving back and forth. And I'm going to say to the right is positive.